Currently, one of the most powerful analytical techniques in a chemist's arsenal is the NMR spectroscopy device. This is a device that stands for nuclear magnetic resonance spectroscopy, and in its simplest form, it's a device that's most commonly used to map hydrogen atom groups on a molecule. There's some important words there. Map meaning, map. It literally will show you where all the hydrogen atoms are, which ones are grouped together. Not only that, it can show you what the neighboring hydrogen atoms are on either side. And we do say groups because as long as that atom is free to spin, those hydrogens will be equivalent and will be grouped together. There's a typical device. They've gotten much smaller and much cheaper, and this is perhaps the smallest one I've ever seen. I pulled this off of Amazon. It costs about $6,000, and anybody in this field knows that that's just insane when you compare it to what they used to cost and how big they were. The important parts of this device are right in here, where the sample, which usually is sort of a glass straw with a cover, is spun, and you have some very powerful magnets. This one probably not so much so. The more powerful the magnet, the more highly resolved your peaks are, which can get very important. So the best devices just have insane superconducting magnets. And what occurs is, once you influence these atoms in the presence of a strong magnetic field, certain ones of them, notably hydrogen atoms, will align. Their spins will align, right? Pauli principle, they've got spins and they'll align. And then as they relax, they will then give rise to peaks that are extremely location dependent. You can spend weeks going into the details of what I just said, but this is enough to give us an idea of how you end up with a map. And since you have a map, you're going to end up with each hydrogen atom, and these are typically organic substances that are in different regions. So let's work our way from downfield. I don't have it written here, but you might want to put a D and a U here, downfield, upfield. At the end here, beyond 10, and oftentimes these things sort of stop at 10. You have the carboxylic acids right there. Around 10, you have aldehydes. The aromatic region is 6 to 7. Amines will be in the region of 6 to 7, but for alcohols and amines, I always worry about moisture. You can get false positives there. Double bonded hydrogens are in the 5-ish region. Heteroatom regions, like having an oxygen or a chlorine or a nitrogen, gives you those hydrogens shifted downfield to about 4 ppm. That's the units that we use. And the completely upfield protons are things like alkanes and things like that. So that's how it works. Here's a couple of pieces of information I'm going to throw at you that might not make sense at first, but they're the key diagnostic things to keep aware. Those hydrogen absorptions that you're going to get split. And they get split in an extremely predictable pattern. It shows up as neighboring hydrogens plus 1. Once I show that to you by example, you'll see how that's a truly powerful technique. Do watch out for symmetrical regions on molecules. That's a little bit of an advanced technique, which I won't go too much into, but it does show up a lot so that you think you have a CH3, but you have 2 of them in identical regions, and they're just like, it's twice as big. All right, so here's a typical NMR spectrum. This is bromoethane. Here's what it looks like. First thing I want to point out is you want to ignore that peak at 0. That's an old-fashioned technique for aligning your instrument. It's a tetramethylsilane, fine, whatever, just don't worry about it. If you see one at 0, that's what that is. Excuse me. Okay, now I see all these cool splitting patterns, but it's usually easier to focus first on the areas. This CH2 group, both those hydrogens are free to spin, which means they will be on average equidistant from that bromine and that methyl group. So they're in the same chemical environment. They'll give rise to the exact same peak. Same thing with this CH3. In general, if you type out the structure typewriter-wise, right, a condensed formula we call that, it'll show you the regions that you're concerned about. Now, a typical NMR instrument will integrate that peak, which means it will mathematically determine the area, and you'll see this like line with a curve and a curve. This one doesn't show it, but I will tell you that the areas here, and I hope you can see part of that. It might be off scale. That says 2, and that says 3. See how powerful that is? That means this must be due to the 2 hydrogens, and this must be due to the 3, since the area is proportional to the number of hydrogens. So we've got this peak for the CH2 and this one for the CH3. Let's talk about this splitting pattern. I see this split into 4 regions. We call it a quartet. I see this split into 3 regions. We call that a triplet. And they're also in these chemical regions here. Notice that this CH2 is next to a halogen right there, so it's in the 3 to 4 region. This CH3 is a garden variety alkane just next to another one, so it's pretty far upfield. And that's that. And if we sum it all, we can say this is a 2H, right? The area is 2. The splitting is a quartet. The location is 3.7 ppm. Try that for this one. You should be telling me that that is a 3H triplet at 1.8 ppm. Now, let's make sure this splitting pattern makes sense. Does this CH2, should it split into a quartet? Well, here's the rule. The splitting equals neighboring hydrogens plus 1. No neighboring hydrogens on this side, but 3 on that side. Add 1, you get a quartet. This is important, so make sure you understand that. Try it again for this one. This CH3, should it split into a triplet? Well, it has no neighbors on this side. It's the end of the road, if you will. But it has 2 hydrogens on the left. You add 1, and you get a triplet. You should be able to apply this to all of these substances now. And by the way, if this triplet quartet thing confuses you, here's a handy sort of map. Singlet, doublet, triplet, etc. 8 or so is about the maximum you can reach, and sometimes beyond that it's such a mess people just say multiplet. Tell me the size and splitting of each of these substances. If you need to review your skeletal structures, now's a good time to do that. But hopefully you'll see the substance, I believe this is called neopentane. That's a CH3, 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 CH3. And since it's just a quaternary carbon with no hydrogens in the center, there's no splitting anywhere. Every single one of them is a 3H singlet. Try that for this one. This is CH3, so it's 3H. You can just do the sizes first. Size is easy. 3, 3, 0, 1, 2, 3. And if it's 0, it means there's no peak at all. So these ones have no hydrogens, but remember, splitting equals neighboring hydrogens plus 1, so they'll each show up as singlets. How about that one? That's a 1H. Now do both sides. None on that side, 2 on that side. Add 1, you get a triplet. 1H triplet. Try these. I hope that you're getting 2H quartet. No, I forgot to add it. That's 3 plus 1, so that's quartet. Add 1, you get the pentet, and that is a 3H triplet. All right, try all these. This should be doable at this point. 3H singlet. 1H doublet. None on that side, 1 on that side. Add them up, you get add 1, you get a doublet. This is a 1H singlet. 1H triplet, does that make sense? 1H, 1 on that side, 1 on that side, add 1, you get a triplet. And we got a 3H singlet there. I'm going to go over each one of these without explaining it, since I hope at this point, I'll explain a couple. I hope at this point it's getting pretty clear. Okay, working our way from left to right. 2H singlet, 3H singlet, 2H triplet, this one, 2H, right, CH2, 2 on that side, 3 on that side, and add 1, I get a hextet, 3H triplet. Over here, 3H singlet, I think I go clockwise, 1H doublet, 1H doublet, 3H singlet, 1H doublet, 1H doublet. You should be noticing some symmetry. I'm going to comment on that in a second. And similarly here, 1H quartet. Let's make sure that makes sense. 2 on that side, 1 on that side, quartet. 2H quartet, 2H pentet, 2H pentet, 2H quartet. Convince yourself those are all true. If you're studying for a test, do a lap through these and make sure you got them. Now I can just imagine Professor Dimmick and others that I had just rolling over saying, this is so wrong. And they're kind of right. It is wrong. To a first approximation, everything here is true. But here's why, if you actually look at the spectrum here, you're going to see some different things. Now, since you're just learning this for the first time, I don't want to dwell on that stuff. This is all true. But here's some things to keep in mind. This thing is tetrahedral, meaning every single CH3 is equidistant from the others. They're all in identical environments. You're not going to get 4 peaks. You're going to get a 12H singlet. And you won't know that it's 12H because it's not relative to anything else. You'll just get a giant singlet. So you have to watch out for exactly overlapping regions. This one, perhaps not so much so. These might look symmetrical, but due to the nature of this double bond, this one is closer to this than that one, so I think you'll get separation there. Oh my God, so much symmetry. That one's going to overlap with that one, things like that. This one, perhaps no overlapping. This one, insane amounts of overlapping. Look at that plane of symmetry there. Similarly here, we have a plane of symmetry there. So, first thing is that you do have to watch out for those overlapping peaks. In my class, you'll get a full credit for at least showing this. It's a good place to start. The other thing that most NMR spectroscopists would be saying, about would be that, well, you know, as long as that thing's free to spin, they're going to be in identical regions. But when you form a ring, most notably like this one, that's spin locked. That thing, if you actually make a molecular model of it, you'll realize that those hydrogens cannot spin. And therefore, the hydrogen that's going into the plane of the board is in a different region from the hydrogen that's coming out, and that's the end of the story. So you'll get more complex patterns. I don't want to go there for a beginning lesson, so I just want to point it out. So those are the two caveats. Many of these peaks will overlap exactly, and if you have a cyclic or a multiple bond, like this hydrogen that's here, is spin locked. It cannot spin around. Make a molecular model to convince yourself it's true. And so that hydrogen up there will be in a different region from that one. And so cyclic and multibonded structures are spin locks. They're going to be more complex, but you know, wait till college for that. Let's draw an NMR spectrum of ethanol and one of 2-butanone. Now here I'd like you to give it a shot. Draw 0 through 10 ppm and figure it out. What I recommend you do is just put a little space, just draw the size and the splitting of each one, write it out, and then map it. Okay? So let's do that together. This is sizes. Let's do sizes first. They're so easy. 3, 2, 1. 3, 2, 3. So it'll be a 3H splitting. I hope you can see that this is a triplet. Region, it's not next to anything that pulls it down. It's just a plain old alkane. I'd write it about maybe 1.5 ppm. Here I would draw a 2H. Ooh, it's next to an oxygen. That'll shift it down to about 4. And is it split? It is. On this side, it's split into a triplet. Now this hydrogen here is separate from there. That oxygen is almost like a separate house. It doesn't typically influence the splitting. So I'm going to do a 2H quartet. And this H will just be a singlet. Now they just wander around. They draw it here, but see how there's that huge region? That's due to any moisture can shift it like crazy. So just draw a singlet 1H somewhere. So again, 3H doublet. 3H triplet about 1 ppm, 2H quartet about 4 ppm, and a 1H singlet maybe around 4. And there they are. Try it for this one. Let's pause this and give it a real shot. I hope you did, and I hope you're saying to yourself, 3H singlet. Hopefully you recognize that that must be a carbonyl. It's the only way you can have no carbons there. And that's a 3H singlet next to a carbonyl, puts it at around 2, 2.5. So I'm going to do a 3H singlet at about 2.5 or so. Here, nothing. These hydrogens here will be a 2H triplet at about 4 ppm. This will be a 3H, did I say triplet? 2H quartet, add 1. 2H quartet at about 4 ppm. This will be a 3H triplet at about 1 ppm. Put it all together, you should have drawn something like that. There's your 2H quartet, that one. There's your 3H singlet, and this is your, let's see, at 1 ppm, that's your 3H triplet right there. Okay, that is an introduction to NMR spectroscopy.